Good morning, students. And today's topic for discussion on the operating systems is CPU scheduling. We've learned about what the CPU is, and we spoke in our last lecture about the importance of scheduling. Now, we'll look at CPU scheduling and we'll look at some of the criterias and the algorithms that are part or the algorithms that are applied to CPU scheduling. In CPU scheduling, there are two types. We have the preemptive and we have the non-preemptive. Under the preemptive, there are different algorithms, and under the non-preemptive, there are also different types of algorithms. Okay, so CPU scheduling is the basis of multi-programmed operating systems. And under this topic, we'll introduce ourselves to the CPU scheduling concepts and CPU scheduling algorithms, and some of the problems that are connected with selecting an algorithm for a particular system. So now let's look at this. In a single processor system, the CPU has to complete a process before another process is scheduled. Okay, but in the multi-programming system, we have the goal of achieving CPU utilization, meaning the CPU has to continuously be executing or working, even if it's in the background. So multiple processes are kept in memory. So if a process has the CPU and its state changes to waiting, it means it's waiting for I/O resources. And the CPU is taken away from that waiting process and handed over to another process. Yes. Um, we discussed about CPU bursts. Yeah, we have the CPU bursts and we have the I/O bursts. So in through a process execution cycle, a process can go through multiple CPU bursts and it can go through multiple I/O bursts in between. And this usually allows for the CPU utilization to be implemented because other processes are able to get the CPU whilst the process that had the CPU is waiting for I/O resources. So this is how CPU scheduling occurs. So new means an application or a program is converted to a process, is admitted into the ready queue. So while it's in the ready queue, it can either the scheduled dispatcher can assign the CPU to it, or there can be whilst it's running, there can be an interrupt. Now, while it's running, there can also be a request for I/O resources. So it goes into the waiting state. Okay. Then you have the terminated state. So all remaining resources are deallocated and the process is terminated. Okay. Very good. So what are the goals of CPU scheduling? It is to maximize the CPU utilization. We have to keep the CPU working all the time. CPU's design was mimicked after the human brain. Because with the human brain, when we want to learn something, we have to continually pursue at it until we get it. And once we get it and we still continue to pursue at it, we find easier ways to be able to implement it or explain it. And that's just how the CPU is. As the CPU keeps working, the CPU keeps learning. The CPU keeps working, the CPU keeps learning. And it makes it start working efficient enough for the user. Okay, so we maximize the goal of CPU schedule is to maximize the CPU's utilization and is to minimize waiting and turnaround time. The time a process uses to wait in the queue to get the processor to execute. And turnaround time involves all the time that is involved when the process the application becomes a process, is incepted as a process. Okay, so we try to minimize these times, and if we minimize these times, we are able to improve multi-programming in our systems, and it ensures the fair allocation. CPU scheduling ensures the fair allocation of the CPU. We looked at something that was called race condition. Then we saw the critical section problem. Then we ended up looking at starvation, which leads also to deadlock. And we saw that having CPU scheduling algorithms is necessary to avoid some of these problems. So it makes sure that no process is being cheated out of CPU allocation. Then it optimizes throughput and response time. Throughput is the unit of work, the amount of work per unit. Okay, so it optimizes it, it gives us the best throughput, and the response time is improved quite a lot. All right. Now, the types of scheduling are preemptive scheduling, and preemptive scheduling allows interruption of a running process to allocate CPU to another. So something like priority, um, round robin, it happens with these algorithms because we know priority, you're given a priority number. So the process with the highest priority gets the CPU, but what ends up happening is that there is something called aging, and aging happens with priority algorithm. So the longer the process is waiting for the CPU, the algorithm increases the process's priority number, and it is able to what also get access to the CPU and complete its cycle of execution. Okay. And we have non-preemptive. So with non-preemptive, once a process allocates the CPU, it runs to completion. So basically, nothing interrupts it. So if you have first come, first serve, so the first process that is selected from the queue is handed the CPU, and it executes in its entirety unless there are IO bursts in between the CPU bursts. Yes. And you have the shortest job first, and the shortest job first, it selects the shortest job amongst the processes, and it allows it to execute. So on the non-preemptive, right, we have FCFS, which is first come first serve, and the processes are executed in the order they arrive. Yes, in the order they arrive. So you can tell that this is a form of a queue, because with the queue, we form the queue. Well, we push the first person, so it's the first in, first out. Yes, we use the FIFO. Yes, so processes are executed in the order they arrive. It's simple and easy to implement. And some of the disadvantages are that there's a convoy effect. So long processes delay others. So if you have four processes, the first process needs 10 milliseconds, second process needs 15 milliseconds. You have a third process that needs maybe 35 milliseconds, and the next process needs 2 milliseconds. You realize that the process that has 35 milliseconds will have to complete its execution before the final process that needs 2 milliseconds. Okay. Yes. So it delays others and has a poor average waiting time. Now, non-preemptive, we are also looking at shortest job first or shortest job next. And it is a non-preemptive or preemptive. So shortest remaining time first. So processes with the shortest burst time is executed first. So as we know, we have CPU bursts and we have IO bursts. So we say that the process with the shortest burst time is executed first, and it minimizes average waiting time. So processes don't have to wait in the queue for too long, and it requires knowledge of burst time and there's starvation for long processes. And we all know about priority scheduling, and it says these processes are assigned priorities. That's priority numbers. So CPU allocated to the highest priority process, and it is used for real-time systems. Starvation of low priority processes, that's one of the disadvantages, but we can use aging to mitigate the starvation. Like I said, aging is a situation whereby processes that have waited in the queue so long end up getting their priority numbers increased. So eventually, we can cut down the waiting time. Yes. Then we have the round robin. The round robin is preemptive and it has a fixed time quantum to the processes in cyclic order. So when we say fixed time quantum, we could say defined time quantum to DTF or time slice. So it gives each process an equal or an unequitable time slice. So the time slice could be, let's say, 4 milliseconds. So once the process gets it, it goes through its executions for 4 milliseconds, depending on the bursts, the number of bursts it has. Yes, it has 4 milliseconds to execute. Then it is switched over to the next one. So there is overhead cost with context switching. Yes, and also the performance will depend on the defined time quantum or the time slice or the time quantum size. All right, and it is suitable for time sharing machines. Then we have multi-level queue scheduling, and the processes are categorized. Okay, they are put into different types of queues, multiple queues, and each queue will be associated with what? A different scheduling algorithm. So if we have three queues, we can associate one queue with FCFS, first come, first serve. We can associate the second queue with round robin, and we can associate the third queue with priority. Okay, yes. So each queue has its own scheduling algorithm. It is flexible for different process types, and but it is complex to manage. Um, Then we also have the earliest deadline first, and which is also preemptive. And it says the process with the earliest deadline gets priority. So it's a form of priority, and it is optimal for real-time deadline systems. And it has a high computational overhead. That is this extra cost that is involved, not cost and financial, but when we say something is expensive in computer science, when we're dealing with algorithms, it means that it goes through some processes or some techniques that adds on to the waiting time or things like that. Okay. Yes. So high computational overhead means there's a lot of computation that happens, and this computation becomes an overhead. So it is not inclusive of what the execution time. Yes. So, what are the criteria for scheduling? So, an algorithm may favor some processes over others, and that's why there is criteria used for choosing the right algorithm. One is CPU utilization, and the CPU must be kept busy at all times. So, conceptually, CPU utilization ranges from 0% to 100%. However, in a real system, it should range from maybe 40% for lightly loaded and maybe 90% for lightly loaded. So CPU utilization is one of the scheduling criteria. And we have throughput. Throughput is the number of work that is completed per unit. So that should also be a criteria to be able to select the right algorithm. So we say CPU utilization and we say throughput. And then there's turnaround time. And turnaround time is the time it takes to complete a process. Is the interval between time of submission, that is the time the process is incepted, that it becomes a process new, to the completion of the process, plus the waiting for it to get into memory and waiting in the ready queue, executing on the CPU and doing IO. So that's turnaround time. So you look at it as turnaround time, the time the process gets incepted throughout all the way till the process completes its execution. All right. So ignore this. I've repeated it. Then you have waiting time. And waiting time is the sum of time spent by a process in the waiting and ready queue. So CPU scheduling algorithm does not affect the amount of time a process executes or performs its I/O operations. So we are saying that the criteria for CPU scheduling has to do with CPU utilization, has to do with throughput, has to do with waiting time, and it has to do with what? Turnaround time. Yes. So CPU scheduling is a very important part of operating systems. It enables us to schedule our processes in a way whereby resources are equitably distributed and every process gets a fair share of the CPU in order to improve, optimize performance, and also reduce turnaround and waiting times. Okay. Yes. All right, guys. So I think we're gonna leave it at this part, and we'll continue in our next meeting to talk about some calculations that are involved in CPU schedule. I hope you have a wonderful day, and thank you.